And good morning, friends. Good afternoon, good evening, whatever it is where you are. I have a couple of reminders. PLC 6 is the review. That is due tomorrow, so an easy one to let slip through the cracks. So please make sure we've got that finished up and ready to go. And just a reminder that homework 3 plus the first celebration will occur on Thursday, which is 1 week from today, Thursday next week, and we will be finishing off our discussion on diffraction today. So that'll give you the full week's time to work that through. Lab I'll be posting tomorrow. Will also be on some diffraction, and you'll get to play around with the diffraction gratings that you have in your lab kit. So we're going to go ahead and get started. Oh, it's way over here. We're going to go ahead and get started and talk about a couple of extra offshoots of diffraction and some interesting properties of gratings. And in fact, we might start a little bit of thermo today. Who knows? It's all just craziness over here. So what we have is a lot of conceptualizing of single slit diffraction. And so what I want to talk about is the effects of multiple sources on one side of the slit that are emitting light and making patterns on the screen. So the way we've been drawing it is that we've had just the one source that has been out here on the left side of the screen. I should say left side of the slits. And so we have just the one source that's making the light, and the light passes through the slit and then makes a pattern. Okay. We then have taken that one source and we've looked at 2 slits, we've looked at 3, 4, 5, multiple thousands of slits. We've looked at a lot of different cases here and we've tried to describe what's going on. Now, what if we go back to the single slit case and we look at 2 sources? Suppose I have a source, and again, these are not to scale drawings, okay? This distance is, I don't know, maybe a meter or 2, who knows, something like that. It's a reasonable distance. I'm intending for the sources to be much further away than one. I'm going to only basically be able to draw them about 1 screen distance, but nonetheless, I'm imagining these sources might be quite far away, and they might be a source like this. Number 1 is up here, and number 2 is over here. All right, so we have 2 sources now. And if we look at what the pattern is going to be on the screen, well, it's not going to be any real huge surprise. We have been discussing what happens when light is incident, basically in a basically with parallel waves coming in. They're all coherent, and they're all coming in. We kind of assumed horizontally, right? Well, now I'm kind of thinking about, if I were to look through the slit, I wouldn't see source number 1 until I was way over here, right? I'm looking through the slit this way, and I wouldn't see source number 2 unless I could see straight through this way. So ultimately, that's where the peaks of their central diffraction maxima will be, right? So since I've taken the light and number 1 I've put up here and number 2 I've put down here, well, what that means is that the light that is coming through here, right? This thing's emitting in all directions, but the straight horizontal, the forward light's getting blocked. So the light that's making it through the slit is kind of down at an angle like this. Okay, so we might say that light from source number 1 is coming through kind of like this. And it's making a diffraction pattern at that point. So its central maximum might be about there, right? All of the light that's coming through here is going to maybe be peaking about here, so we'll say, so we'll say pattern number 1 is going to be somewhere over here. Good. Yep. Okay, so there's the pattern from source 1. The pattern from source 2, that we might say is going to look something more like as if it's coming through here, maybe somewhere up here. So pattern from source 2 might look like that. And so the question I want to address is, number 1, are these two patterns resolvable? Okay, so what does it mean when we say something is resolvable? In other words, can I distinctly detect two different sources? How do I distinctly detect two different sources? Well, I go over here to the pattern and I say, are the central maxes well separated, right? Is there one that's clearly over here and one that's clearly over here? And the answer in this case, I think you can see, is yes. These should be clearly resolvable. These peaks are widely separated, right? So the question then comes in, well, where is the dividing line between something being resolvable and something being not resolvable? All right, a situation where I take these two sources, and again, I want to try and imagine these like kind of more far away than I've been able to draw them. And if I take them further away, you're going to notice that the angle kind of shallows out, right? By the time they get to here, that's going to be a little bit more parallel. So that's going to start bringing the peaks closer together, okay? Same idea if I just take these two things and I just kind of squish them closer together, right? If I start pulling them closer together, the angle that they make is going to be lower. Right. In other words, when I talk about the angle, I'm talking about this angle right here, the angle that these are making, these rays are making with each other. So the question comes as to when are they going to be kind of on the cusp of being not resolvable? In other words, I look at the screen here, say, and I can't quite distinguish two separate diffraction central maxes, right? I cannot distinguish these two. When that happens, I'll say that they are not resolvable, and that what that basically means is that the light coming through here is making these two things appear to the screen as if it was one, more or less one kind of like extended object, maybe. It might seem kind of elliptical. So that question is answered by thinking about when I scoot these two peaks together, when do they become not resolvable? Okay, so here and here, this distance is definitely resolvable. And if I look at the peaks and I say, all right, well, what's the criterion such that the pattern on the screen makes it seem as though there's only one source? As these peaks get closer and closer together, the very, maybe you would say the tipping point, is when the peak of one lies within the diffraction minimum of the other, the first diffraction minimum, right? Because at that point, this peak would be atop this, say this red peak would be atop this blue minimum right here. And then if I started scooting them even closer, then the red peak is starting to overlap with the blue peak. In other words, the central maximum, this central diffraction maximum is now overlapping with this central diffraction maximum. Whereas if I had the, and what I mean by that is that the central, like the absolute central constructive interference, right? Because we know the peak has width. And even if the peak of this one is overlapping with the minimum of this one, the peaks are overlapping a little bit. But I'm talking about where the actual peak here When that actual peak starts getting into this one's central diffraction maximum, that's when it starts to look like, well, I can't tell the difference between those two. Okay. So what we would do is we can draw several pictures here, and I can just kind of start drawing situations where we scoot these a little bit closer together and try to draw what the pattern looks like. All right, so this is a situation which I hope you agree is definitely resolvable, as these peaks are widely separated. Now, if I take these two here, I'm just gonna keep scooting these a little bit closer. Let's say source number 2 is now moved to here, and source number 1 is now moved to here, like so. And I've drawn them different sizes there. That is not meaningful. Okay, so now when I think about the light coming through here, I'm going to draw these peaks now opposite the slits, or opposite the places where they are on the other side of the slit. So, for example, source 2 now is coming through here, or the majority of it here. So we would say source number 2 might look something like that. Source number 1, we might say it comes through kind of like this, and that means source number 1 might look something like that. And now I would say these are barely resolvable. Okay, these are barely resolvable. That is to say, this one here, that peak right there, and that peak right there, see, this peak is lining up with that diffraction minimum. So we've got a situation where, yes, the peaks are overlapping, the maxima are overlapping, but the centrals, like the very bright pieces, you can definitely see there's one there and there's one there. Yes, there's a little bit in between, but these two are definitely resolvable. Anything past that, and then you're going to start saying, no, I'm not going to be able to tell the difference. All right, so that would be a situation where I'm going to squeeze these even closer together, and then all of a sudden I've got a peak here and a peak here, and it's just becoming one big mess. Okay. Okay. So I could draw that on there, but I think you understand what that picture is going to look like. So let's put this into an optical standpoint here. Well, actually, no, let's not do that. Let's talk about the criterion first. So the criterion is known as Rayleigh's criterion. After someone by the name of Lord Rayleigh. And he was kind of one of the first people to put this into context. And say that two sources are distinguishable or resolvable. That's a lower word. When one peak lies at the minimum, or the first diffraction minimum of the other. Okay. So that is the criterion. Now, it is predicated on a couple of things, which is that, now, as I've drawn it here, it would be nicer if these peaks were a little bit more peakish, such that the drop off here was a little bit more, so their intersection was down here. Because the way I've drawn it here, you'd say, well, there's light coming from the number 2 source, and its intensity on the screen follows the blue line here, which is that. The light from the red source comes here, and it falls, and its intensity on the screen at the same point as that. So actually, these two here are going to add up to be greater than the peak of either one. So the drawing is not perfect. The idea is that these are still the brightest pieces that you're looking at, and any time that these peaks get closer together than that, that's when these two start lining up enough addition to overwhelm what the peak of the diffraction maximum looks like for either one of them. Okay, so like I said, I know I've drawn it such that this piece here, the blue intensity and the red intensity, would add to be something out here. It looks like it would be double that. Yeah, it would be almost a peak. So it would look like kind of a washed out situation here. So note that the peaks should probably be slightly slimmer down, a little bit more peakish, right? So that is not a situation that's happening. What we want to be happening is that this point on the screen with this intensity is clearly resolvable from this one, because none of the blue source 2, none of that blue source light is affecting the intensity of this point on the screen here, this peak. Right? So in order to do that, we'd ask, well, okay, well, what's the what might be the minimum angle here? What's the minimum angle here whereby we still get resolution, right? Well, that is basically like asking, what is the angle between the central diffraction peak maximum and the first diffraction minimum of that same pattern, right? In other words, this one here is lying directly in the diffraction minimum of that one there, just as this one here is lying directly in the diffraction minimum of that one, and therefore the angle that's going on is the angle from the peak, either one, to its diffraction minimum, its first diffraction minimum, which is right here on the side. So we are fairly well aware of what that's going to look like. That's the situation where the angle, called theta minimum here, is equal to lambda divided by A, because we use the minimum condition of A sine theta equals 1 times lambda, and we just rearrange it to look like this. Okay? So this situation gives the minimum angle, right? And for situations where the angle is small, in other words, that lambda over A is much less than 1, which is typical for visible light, what we would say is that theta minimum is just equal to that. We might say it's pretty close to lambda over A. And we'd call that the Rayleigh angle, or the resolving angle, or the minimum resolvable angle, or something like this. Okay. All right. Now, let's extend this to seeing with our eyes. Of course, we have a pupil, which is a circle, more or less, unless you are a goat. That's really weird. Goat pupils? I had heard about goat pupils, and then maybe 5 to 6 years ago, we got some goats. So naturally, I had to go like, hey, is it really true? Yeah, it's really true. They're weird looking. They're like rectangles. It seems like it shouldn't be a natural phenomenon. It shouldn't be a naturally occurring thing for something to have like square or rectangular pupils. Really weird. Anyways, ours, thankfully, are not. So what we're going to do, instead of a slit, it becomes an aperture, right? Just a hole. Aperture is such a fancy word for just a hole through which light passes. Okay, and that means that we would like to come up with some way of describing the effective slit width of an aperture. Now, I don't want to go through a whole bunch of this as to why this happens, but there's a little bit of experimentation, a little bit of geometry, and instead of something having a slit width like this, if you look directly on, if I, in other words, took a look from this perspective here at what the slit looks like, what am I drawing? I'm drawing something like this, where these are blocked out and the slit width is just this. What we're asking then is what happens if instead of that, right? And of course there's vertical extent to it as well, right? It caps off, say, here and here. So what happens if I have this diameter, I have a hole, I have an aperture, right, of the same width, maybe like diameter D. Oh, I probably shouldn't call it D. That's what the slit separation is. Okay. We'll just call it 2R then. 2R, twice the radius of this hole, of this aperture. So we come up with a relationship between these things. Man. How about, gee whiz, I don't want to call it little d, and I don't want to call it capital D. Too bad, I am going to call it little d. Too bad. We're going to do that. So what I'm going to do is I'm going to look at the amount of light that would be let through by an aperture versus the amount of light that lets through by a slit. And I'm going to look at the geometry of the situation, blah, 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 blah. I'm going to do a bunch of work and find out that the slit width is related to the diameter by just a numerical factor. So it's really just an easy transition from one to the other, all right? In other words, when I try to write the slit width in terms of the diameter, what I come out with is that D I would come out with something like this. Okay? That the slit width and the diameter are related by just a numerical factor. Okay? And that the diameter of the thing, in order to let the same amount of light through, okay? And it sounds kind of weird the way I'm saying it, but in order to have the same effects, I would need to multiply by this 1.22. I would need to multiply the slit width by that factor in order to get the diameter. So this resolving angle down here, this theta minimum, basically becomes, if I'm solving this for A, I would swing this underneath, and then I would take that whole expression and put it in there for A, and I would say that the minimum resolving angle is something around 1.22 times lambda divided by little d, where d is the diameter of the hole. Or if I'm aperture diameter, for those of you who like the $5 words. All right. Okay, so let's take a look at a situation where we're looking through a microscope with particular wavelength of light, and we are wondering what is the minimum resolvable angle. Okay. So we're going to do an example where we're going to use a microscope, and I'm going to look through a microscope, and microscopes are there to make things bigger, which means that all the stuff in there is really small, and this is a really useful thing to know when you're using the microscope. You want to know how close can things be when I'm looking through the microscope. And I can still make them out and still make sure that there are two things there, not one. So if I have a microscope and I'm illuminating it with sodium, and sodium light has a very well-known bright yellow wavelength. It turns out to be just about that wavelength in nanometers. And I'm looking through an aperture. Microscope has that light wavelength and an aperture diameter of, for example, if you look at the eyepiece, diameter aperture of, say, 0.9 centimeters. So we'll just find theta minimum from that. And then we'll make a couple of adjustments to it and ask what's the absolute minimum possible angle, what would happen if we submerge the whole thing in water, etc. All right, so we'll play around with it. We'll get this number, then we'll play around a little bit with it. We'll find theta minimum to be approximately equal to 1.22 lambda over d. And once again, we're going to have to make sure that we match up our units well enough. So what do we want to do here? 589. If we use 589 times 10 to the minus 7 centimeters, then I could just divide by 0.9 centimeters. Right? Normally you would say, I'm going to do 589 nanometers, so you might do times 10 to the minus 9 meters, and you could do times 10 to the minus 2 meters here, but ultimately, with that factor of 100 off, you get minus 7 centimeters in the nanometer scale. So our minimum resolving angle here is, as you're going to imagine, pretty small, right? It's going to be pretty small. It's going to be in the 10 to the minus, I don't know, you're going to get, that's a 5, and these two are approximately the same thing. So it's going to be somewhere in the 10 to the minus 5s. Let's see here. In fact, I think I may have calculated this. And I did. It's about 8. It's about 8 times 10 to the minus 5 radians. Okay. Now with our pupil, okay, so that's just coming through the microscope itself, right? That's just coming through the microscope itself. With our pupils are going to be a little bit smaller, right? So in other words, the diameters of our pupils probably not 9. It's probably not a centimeter in diameter. So this number is going to be slightly smaller for our pupils, which makes this number overall larger. And that means that if it's barely resolvable at the microscope, right in the microscope level, through the lens, the eyepiece of the microscope, then we might not be able to resolve it through our eye, right? Because if the minimum angle for our eye is greater, that means that anything less than that, we're not going to be able to resolve. And if this is less than that, because it's coming through the microscope thing, then we may not be able to resolve it. So something to think about. This, however, is a relatively small angle in the milliradians, almost microradians situation here. That's a really small angle. So that's probably not going to be limiting things, all right? For example, one question we might have is, what would be the absolute minimum visible angle that could be found here? Well, when I'm talking about the minimum visible angle, then that's a wavelength situation, okay? So that would mean this is a nice bright yellow. If I wanted the very minimum possible resolution, I would set that to about 400 for blue, because past that, I say we don't really see past 400 on the lower side, right? So if I used 400 nanometers, that would be probably what you would describe as a fairly deep blue. So with that being 400 nanometers, you would get something like theta minimum here is going to have gone down -5 radians, is going to have gone down even a little bit further, because remember that as you decrease the wavelength of the light and leave the slit width the same, then the pattern gets more sharp, right? In other words, the pattern gets sharp. Well, I just said that the pattern gets sharper. It compresses a little bit, say, right? It scoots itself in with smaller wavelengths. So the angle at which you could barely resolve two things with that light would also likewise squinch in, because the distance angularly from the central maximum to the first diffraction minimum will be shrinking, right? Okay, so there's a little bit on that. This is how to resolve different things. Now, one interesting thing, this is when you're running up on this limit, this is known as diffraction limiting. If you have a situation where you are becoming diffraction limited, so for example, that's the situation where I don't know, I don't want to necessarily go down this road, but every now and again you'll meet people who are very concerned, and they are concerned that the government is spying on them with satellites. Okay, and it ranges from being able to see what I'm reading, right? If I'm reading a book that is some type of anti-governmental situation here, they might be a little worried that there's a satellite that's overhead watching, or they're tracking their movements somehow with the satellites. So sometimes what's a useful situation is to consider how well can a satellite actually see these things. Now, a satellite's going to use a camera, right, in order to take pictures. Well, those cameras are cameras, so they have an aperture, and there's a lens and all this other stuff. But ultimately, there's going to be a diffraction limitation that these things are going to run up against, right? Because they're way up there. It might be 100 miles above, right? And you're looking at something that, if you're looking at the pages of the book, you're looking at the words on the page of the book, right? Then the letters are however big they are. Can a camera from the satellite resolve these individual characters on a piece of paper? So one thing you might ask yourself is, okay, if I can calculate what the minimum resolvable angle is, and then check and see what the angle kind of looks like from that distance, right, based on the triangle geometry, then can we make an assessment of what's happening here? So let's imagine, right, that you have your satellite up here, and of course it looks like a TIE fighter, and way down here you are reading a book with words on the page, and you're asking, can the satellite's camera take a picture of these things? And that means that the angle you're looking at, and I'm not sure that you can resolve that. I have two lines there. Can you see that I have two lines there? Ooh, barely. Okay. Because this camera has a pretty small aperture. Okay, I've got two lines here that maybe you could imagine one goes to the bottom of a character on the page and one goes to the top of a character on the page. Or if you like, one goes to the bottom of the entire page, one goes to the top of the entire page. But if that was the case and you could only resolve that big, then you couldn't see what was written on the page. So let's suppose that this distance, and I've drawn it this way, probably in a not practical sense, but imagine the satellite's directly overhead, right? So that the distance here, this entire distance, from where you're sitting on your park bench quietly reading your book and their satellite is overhead watching you. If it's a low Earth orbit, we're going to talk maybe like 60 to 80 miles. Let's just call it 100 miles. Okay, and the satellite's going to be whipping over pretty quickly. It's only going to be able to see you for probably about 3 to 5 seconds as it goes over. So let's just call this approximately 100 miles. And if this is a camera, there's a camera inside the satellite. Now the satellites are, I mean, they're big, but they're not enormous. They got a lot of stuff on them that they need to pack on, and it costs a lot of money to get a satellite up. I mean, you're talking $10,000 to $15,000 per kilogram of payload, right, to get into Earth orbit. So if this is a standard camera, let's just say standard cameras have about a 1 centimeter diameter, maybe even a little bit bigger. Let's make it a really large camera. Let's make it a big camera lens. Let's go 5 centimeters. That's an aperture, right? A 5 centimeter diameter. Let's see, how big is that? That's going to be like, that's about like that big. That's a pretty beefy camera you got there. All right, let's suppose that the camera has a diameter of about 5 centimeters. What's the minimum angle that we're going to be able to say is going on here? Well, if I think about the character, right? If I think about a character on a page, I'll say, if I'm reading something, I'll say it's about a centimeter. Okay, so I'm looking at something here such that this triangle ends, I'm just going to say down here. The characters are about a centimeter. So in other words, you want to detect 1 centimeter differences at 100 miles through a 5 centimeter diameter camera lens. Can we do it? Well, if I take 100 miles and I take 1 centimeter, and I used miles, so I should probably have said kilometers. So I'll just change that to kilometers so that we have this a little bit easier to work with. I don't know why I said miles. Of course, 100 kilometers is way smaller, but that's okay. We're just an approximation, and this ultimately is even better. So the minimum angle here, this is not the calculation, so I want to call it this. I want to call it the angle. The satellite angle is going to be approximately, right? It's going to be approximately the distance of the character divided by the distance of this. Now that would mean I have a triangle that looks approximately like this, right? Where this is the character down here, and this distance here is 100 kilometers. So I have a triangle that looks approximately like this. Really, I would take double this angle if I'm using the small angle approximation. Okay, no big deal. I would take it's approximately 1 centimeter in 100 kilometers, which is 100,000 meters, which is 10 to the 5th. So this is over 10 to the 7th centimeters. That's 100. Is that right? That would be 100 times 10 to the 3. That's 100 times 10 to the 5. Is that wrong? That's 1,000 meters. Yeah, 100 times 1,000 is 10 to the 5, and I need to change that into centimeters, so that should be 10 to the 7. All right, so this is about equal to 10 to the minus 7 radians. All right, so let's check it against the theta minimum here. Theta minimum is going to be about 1.22 multiplying lambda over d. So let's just choose a normal lambda, say about 500 nanometers, and a diameter of 5 centimeters. So that's going to work out to be 500 times 10 to the minus 7 centimeters. right? So with a 5 centimeter lens, yeah, I'm thinking about fives going away. 100 times 10 to the minus 7 is 10 to the minus 5. So we're in the same kind of range as this one. This is going to work out to somewhere around 1.2 times 10 to the minus 5 radians. And I'm not sure if I'm off the edge of the board here, but maybe I am barely. Yeah, so the resolvable angle is 100 times greater than the actual angle that you're trying to photograph. So there's no way a satellite's going to be able to read pages on a piece of paper, or characters on a piece of paper, right? The minimum angle is about the same as this, 10 to the minus 5, and that's much less than that, right? So I guess now you can start to walk with some confidence that government's not spying on what you're reading, at least with satellites. Now, maybe with the spy planes that are invisible, that's a different story, but I don't know if we can go into those. Okay, so a little bit on resolution of objects at large distances. All right, so when you have the large distance, you're thinking about making a triangle with it, somewhat like I've just done here with a length and an opposite side, and you say the angle is about whatever it is, right? So it's approximately equal to the tangent. All right, so good. I think that is probably about as much as I really have planned on here. So in terms of optics, we'll just take a quick look here. We'll just take a quick look here and say what topics have we looked over so far? All right, if we start back at the very beginning, there were two laws. When we talked about the ray model, there were two laws, reflection and refraction. And then overlying those, we eventually found there's a principle, right? Least time principle that we can think about. So this kind of helps us put those two laws in context. We explored, well, there's not much to explore with reflection, but we explored specular and diffuse. And with refraction, we explored refraction as well as total internal reflection at the critical angles. All right? We used those to talk about mirrors and lenses, and found that the mathematical description of these was approximately the same because the geometry of the situation was approximately the same. When I looked at the ray drawings for these things, these would come out with three principal rays that we wanted to concentrate on, and the mirrors and lenses, they basically had the same geometry. It was just that the mirrors kind of folded the geometry onto itself, whereas the lenses were passing the light through, so it was kind of more an extended situation. We did combinations of these when we looked at the telescope, when we looked at the microscope. We looked at angular magnification, right? So magnification to go along with these, as well as the focal length and the image locating equations. We talked about the lens maker equation for the lenses. And after that, we moved into the wave model, which we talked about the three modes of interference, or the three mechanisms of interference. There are three, or I call them three reasons as to why we had interference that we were going to talk about, right? They all came to bear when we talked about the thin film. So the thin film is like the capstone, right? It's the one that encompasses all three of these things. So we didn't talk about it first. We did talk about double slit. That's really only a situation in which we are concerned with the path length difference. Thin films, all three. right? We talk about interference of many waves, which is known as diffraction. And so we came up with the single slit. We also applied it to the double slit, and we came up with not only location equations to tell us where the peaks are, we also drew the intensity patterns, and we could figure out how many fringes we were looking at. So thinking about drawing the path length difference in a two slit experiment, thinking about drawing waves in a single slit, which are out of phase, but so they cancel, this bundle cancels with this bundle, but this bundle is left over, kind of thing. So intensity, locations, okay, numbers of fringes. These are all things that we talked about. And then we've just ended up talking about the diffraction grating and resolution. And there's more on gratings that we could go through, but I think we did reasonably well enough last time talking about the characteristics of what happens when you look at multiple slits and the individual, the principal maxima, and then the secondary, the intermediate maxima that occur between the principals and things like that crop up. I think we covered that enough that we don't need to go into more about mechanically what is happening, not mechanically, but mathematically what is happening. So as far as stuff we've covered, I think something along those lines, and I may be missing something, but I can't quite think of what it might be. So hopefully that's a reasonably coherent list. And so that is celebration one material, right? So we'll cut it right here and say, this is the end of celebration one material that we're going to have. That means that starting now and then proceeding into next week, we're going to be talking about thermo, and that means we're going to start thinking about PLCs on thermo and some homework problems on thermo, but that also means you still have to study if you need to go review all of this stuff, which, I mean, hopefully it's always good to review that stuff and keep yourself fresh on it. Go take a look at that while we're doing. Alrighty. So just for some smiles and giggles, I did bring in, so this is close to a diffraction grating that you have in your kits. You do have one, you do have one in there. It's about this size. And same thing I would tell you with the polarization, with the Polaroid filters, I wouldn't grab it this way, because then you're going to have your oily fingerprints all over the diffraction grating. So you want to maybe grab it by the edges here. And then you get yourself a nice bright laser like this, and you can put it through there and see that, oops, you can see that I've got it vertical instead of horizontal, and there it goes. All sorts of wonderfulness is happening here. Central bright fringe is right there on the word diffraction, which is appropriate. I like that. I definitely have maxima number 1, maxima number 2. I don't think I can get maxima number 3. Oh, maybe I can. Is that it over there? No, that's not it. That's a reflection. That's a reflection. Where's maximum number 3? Oh, I guess we can't even see it. Oh well. So have a little bit of fun with that on the lab on Friday. But as for now, I think that's enough on resolution. All right, so why don't we do this? I'm going to start a little bit on thermodynamics now because we've got a little bit of time left over, and we'll pick up after lab next week. We'll pick up with thermo on Tuesday and celebration on optics on Thursday, 1 week from today. All righty. So we're going to the second phase of this class. This is the second of three parts of the class that we're going to discuss. And one reason that this is likely a hard class to endure as well as to teach in some sense is because we are moving through topics relatively quickly. So we can only do a little bit for each one. And that means we're going to start with thermodynamics for the next few weeks. And we'll do a celebration on thermodynamics in about another 5 weeks or so, 5 to 6 weeks. We'll do another one, and then we'll start our modern physics about then. This is the end of week 6, so we had 6 weeks on optics. If we do 6 weeks on thermo, that means we've only got 3 weeks left for modern, which is somewhat of a shame, but we will see. We will see. So thermodynamics, as you gather from the name, essentially the study of not just heat flow, but also energy flow. Okay. In this case, this is a really interesting topic because it gives us bounds on what is possible with energy. And the really cool part of this is that it doesn't tell us that you can't do such and such with, say, for example, kinetic energy, but you can do it with potential energy. It's energy, right? So if you think about back to kind of a 4A situation where you learned about mechanical energy in 4A, right? You learned about a ball rolling down a hill, and the hill could be shaped weirdly, but as long as you thought of the initial gravitational potential energy the ball had, and then whatever it came down here, however it managed to come down here, hopefully friction being somewhat negligible, you would come down here with a particular kinetic energy, and it wouldn't have mattered the shape of the hill and all this kind of stuff. Whereas with Newton's laws, it would be requiring the force diagram if the hill is changing its shape and all that type of thing, and then you'd have to integrate to find what speed would be down. So energy is a very nice offshoot. It's a very easy tool to use, and ultimately is one of the most powerful tools in all of science, not just physics. And even more so is the thermodynamics of the situation, which then tells us how much we can expect to get out of energy. And that's a really interesting situation because it's telling us that, yeah, sure, potential energy becomes kinetic energy as the ball rolls down the hill. Can we have a different situation where kinetic becomes potential, and can we do this, can we do that? So how much can we expect that how much of that energy can we expect to recover, right? That type of thing. So thermodynamics is a discipline which is set out by the laws that have been put in place. And so let's talk about the laws of thermodynamics. And that's probably about all we'll have time for today. But let's just start getting a look in at the laws and a little bit of the history of the thermodynamics. So there are 4 thermodynamics laws. And I would say just like Newton, but Newton obviously only has 3. If you include gravitational law, that's 4, so great. Of these 4, we will talk mainly about only 2, okay? The other 2 are more like Newton's laws 1 and 3, and in the sense that you don't calculate with them, but you use them as conceptual tools to guide your thinking, okay? Most of the calculation that happens mathematically comes from laws number 1 and 2 in this sense, okay? So unfortunately, with thermodynamics, it is a relatively screwy subject, so the laws did not come about in chronological order. And so by the time they had reached law number 3, they realized they should probably have a more principal law, and so they had laws 1, 2, and 3, and then realized we need something else. And so it's supposed to precede all of these 1, 2, and 3, so we have to call it 0. So we do actually start with law 0 in thermodynamics. We have laws 0, 1, 2, and 3 for thermodynamics. And if you were interested in the chronology of how these came to be, I will tell you the years. Let's see here. I remember a couple of them off the top of my head here, but let me see if I have these written out here. Law 3. Yeah, okay. So we had, in terms of chronology, we had law 2 first. That was about 1824. Law 1 was about 1850. Law 3 came about in about 1910. And soon after that, in 1930, 1935, we realized, wait a minute, we should have something before all of this. So a good 100 years worth of development here, leading us to the 4 laws of thermodynamics. And like I said, 2 of them are conceptual and 2 of them are more calculationable. So the 2 calculation ones, and ultimately the ones that we're going to spend more time on, are laws 1 and 2. Laws 0 and 3 are therefore what I typically refer to as scaffolding. They are here because if they weren't there, we wouldn't really be able to have a well-defined discussion about some of the principles of thermodynamics. So for context, let me tell you what law 0 does. Okay, so law 0 basically defines what is meant by a temperature. Now you can see that this being thermodynamics, if we can't define a temperature, then we're going to have a lot of trouble talking about how to compare how hot something is to something else, right? We're going to have trouble doing that. Fortunately, by the time 1935 rolled around, we already had a really great idea of what temperature was because we'd been measuring it for 200 years, okay? So 150 years. So law 0 really defines it only in the sense that it gives the context for its usage in the topic of thermodynamics. All right. So if we think about law 0, law 0 basically defines temperature and what is meant by thermal equilibrium. So it does this. It does this by defining what thermal equilibrium is. So defines temperature in terms of thermal equilibrium is what that says. And I realize that we've got a glare issue here, so I'll just go stand right there. Now you can see it. What is thermal equilibrium? Well, if you remember from 4A, or if it wasn't 4A that you took at Cabrillo, then perhaps it was a mechanics course that you took somewhere else. You must have talked about equilibrium because that's a situation where the forces are balanced, right? Mechanically, I got a force pushing that way, got a force pulling this way. Well, they're right? So if they are equal strength forces, then you are in equilibrium. Now, that doesn't mean that the object is not moving. It just means it's not accelerating, right? Well, same kind of thing here. When things are in thermal equilibrium, that doesn't mean that they are at 0 temperature. They could have a temperature, but they could just be exchanging heat equally, right? It could be losing heat from itself as much as it's gaining heat from this thing. And then all of a sudden what that means is I have a constant temperature, right? Just like in forces, you'd have a constant velocity, right, of movement. My velocity isn't 0, just like the temperature doesn't have to be 0. It could be something. So two objects that are in thermal equilibrium so let's suppose that we have two objects in thermal equilibrium. A is in thermal equilibrium with B, okay? Now, let's suppose, and I'll just draw this real quick, so I'll just have an A here and a B. Okay, so there's an A and a B. Now I've got, and I've established that these two things are in thermal equilibrium. Now I'm going to take A and I'm going to go over to object C over here, and I'm going to ask the question. I'm going to make this much different than B, so let's make it much different than B. It's going to be, here is object C. I'm going to now take object A over here, and I'm going to put it right here, and there's object A. Oops, let's make it a little bit bigger so we can see it. Okay, I'm going to take object A over to object C, and I'm going to ask the question, are these two in thermal equilibrium? Now, if these two are in thermal equilibrium, then we come to the conclusion that B and C, were I to have just eliminated A completely, I could put B and C in thermal contact, and I would say B and C would be in thermal equilibrium. All right, this seems on the surface to be a ridiculous law to have, right? The idea of, well, if these two are in equilibrium, and then I take that one and put over here, and these two are like, well, yeah, duh, right? But ultimately, that's what temperature is, right? Just make object A a thermometer. If I take object A, which is my thermometer, and I put it in contact with this thing, and it comes to thermal equilibrium, which that's what a thermometer does, and then I take it over here and it reads the same temperature, and I go, oh yeah, look at this. This is now in thermal equilibrium. Then we define B and C to have the same temperature because they are in thermal equilibrium. That's what the law is getting at, right? That's what this law is doing. So two objects in thermal equilibrium. If I were to abbreviate this, I would say two objects in thermal equilibrium with a third object are in thermal equilibrium with themselves. Now, is the wording of this important? No. Is the philosophy behind it super important? No. It's just what it gives us. Okay, it just gives us an ability to define what a temperature is by saying, are they exchanging heat or are they not exchanging heat? Right? So a thermometer is not in thermal equilibrium with something until the temperature stops moving, right? And so anytime you're cooking something and you want to take one of those instant read thermometers, it doesn't matter if it's one of those or if it's like, I don't know if I can even say the word mercury anymore. A red alcohol thermometer with the little thing that goes up and down, right? Or if it's one of those little instant read. Oh, this is also an instant read. Like kids got, they do at the daycare, right? And they go, boop, oh, it's 100 and it's 101, and they get the little frowny face, and they go, come get your kid. And you're like, how about I give you an extra $5 and you just keep them for the next couple hours? No. Oh, okay. All right, so this gives us the ability to talk about temperature as a result of do two objects exchange heat. All right, so that's law 0, and that ultimately, as I said here, was the last law that was put in place here. Law 1, happy days, you already know law 1. You already know what law 1 is. It's energy conservation. Okay? But don't restrict yourself just to mechanical energy now. Okay? It's not just mechanical energy we're talking about. It's going to be other types of energy because ultimately this is thermodynamics. So law 1 is energy conservation. And like I said, this is going to be one of our principal, one of the principal laws that we're going to work with. So we are going to include thermal energy. And as a type of energy, right? You might say, well, what kinds of energies are there? Well, there's kinetic energy, there's gravitational potential energy, there's spring energy, like elastic energy, right? There's thermal energy. Okay, good. We're going to make sure we include that. Well, there's also nuclear energy and electrical energy and solar energy and wind energy and water and power and wait, stop. Power is not an energy. We're going to include thermal energy, and we're also going to include something called internal energy, which is the energy, as it says, internal to an object. Okay. And we are also going to include different types of transfers. All right. So we're going to include a heat transfer as well as a work. Now, work, you should be fairly familiar with. That's the thing where if I push on something and I do work on the object, then it may change its kinetic energy. You may have learned it that way. I tend to take a slightly bigger approach, which is that work changes energy, because I could certainly do work on something this way. I could do work on it, right? And it would change its gravitational potential energy. So there are basically two types of transfer. Oh, wait, whoops, I forgot to put internal energy up here, sorry. Include thermal energy and internal energy. And the two types of transfer all right, so two types of energy transfer. We have work, which involves a force exerted through a distance, typically, right, in a mechanical sense. And now we are also going to talk about heat transfer. And heat transfers in a couple of different ways. By direct contact, it can be by radiation, it can be by convective movement of a fluid, right? You can transfer heat in a couple of different ways. And work, right, like I said, mechanically, typically a force, a distance, and we're hopefully pretty familiar with that. All right, so law one is energy conservation. And also it helps laws 0 and 1 help us define the system that we're interested in, right? Because if I'm talking about energies transferring, I need to have a system and I need to know the boundary of the system. What is inside my system? What is outside my system? Is the boundary permeable to heat or material, right? What kind of boundary do we have here? Okay, so not just law 0, but also law 1 help us to think about what is our system, okay? And that's a question that is, again, one of these things where when you're first starting out, it's that question that you don't really want to answer because there's no prescribed way to do it, right? Like, I'm teaching you how to add numbers. You always do this, and then you add this, and you can count up to this, right? And there's a prescribed way of doing addition. Well, with a system, there isn't necessarily a prescribed way of doing it. It's recognition of this is the thing that we are interested in talking about, and then thinking about what are the boundaries of that system, right? What is inside that system? What type of boundary is this? Is this a flexible boundary? Is it one in which heat can get through? Can work be done on the thing? Can material pass through? Okay, so these are all mental constructs in some sense, right? I'll give you an example. So when you talk about cloud formation, okay, when you talk about how clouds form and what kind of things are happening in the atmosphere is an incredibly complicated system. Okay, we can't think about it all at one as one thing. And remember, when we first started this class, I was talking to you about what is it that we do. We as physicists make models. Okay, so the system is a simplified model. When we talk about clouds forming, we can take a piece of air down here that's warmer than its surroundings and imagine it going upwards. And the way I think about this is, if you ever had dry cleaning, you get those big, huge plastic bags, right? You just imagine a big plastic bag filled with air. Actually, what I imagine is the air, and then I imagine the plastic bag around it and going, okay, it's this packet of air that I'm interested in. And this packet of air is warmer than its surroundings, and so I'm going to watch it start rising. Okay, it's going to exchange some energy with its surroundings around its edges, right? But it's going to stay warm, and as it moves up, it's going to expand, which is going to cool it off, but it's not cooling off as quickly as its surroundings, so it keeps having energy, right? So it's just this kind of model making that you do in order to simplify the thing that you're talking about, and it's just through kind of doing that and recognizing it that it becomes second nature to you. So I'm going to write the idea here that laws 0 and 1 give us the idea of how to talk about a system and its boundaries, okay? Because those ultimately are pretty important in terms of talking about energy and what kind of energy is going to be coming in. Is energy allowed in? Is heat allowed in? Is work allowed in? We can change these things. Right? We can change mentally in our model. We can change whether or not work or heat can come in or not. Okay, so we've got the system and its boundaries, and we want to think about what is in the system and how are the boundaries allowing the system's variables to change. Okay. The system typically has variables that we're interested in. And these variables describe the state of the system. So I'll give you an example of something that we will work with extensively in talking about thermodynamics because it's one of the easiest possible systems, and that is the ideal gas. Okay? The ideal gas, if you have learned about this, possibly it was in a chemistry class prior, then, I mean, that's great. Obviously, we'll put the correct spin on it for you so that you can get some better understanding out of it and put it in context. But ultimately, the ideal gas is really great to talk about because it's easily definable, right? The variables that describe the state of an ideal gas, what are they? Pressure, volume, temperature, and the amount of stuff that's in there. Okay? So because an ideal gas is so easy to work with mathematically, and it's also very easy to work with conceptually, we're going to spend a lot of time talking about this, right? Okay, so I have a boundary. Can it accept a heat transfer across it? Yes. Okay, well, the temperature might change of this ideal gas system, right? I have an ideal gas in my canister here. If I can put energy into it via heat, well, then in that case, I might see a temperature increase in my ideal gas. I might see a pressure increase in my ideal gas. I might have variables changing, right? So the thing about these energy transfers is that they change the variables that describe the system, right? And the variables that describe the system are typically related to the energies of the system. So we'll talk a lot more about that. It's looking like we are just about out of time for today. So we got through 0 and 1. I will recap these again a little bit more thoroughly on Tuesday, but this is where we're going. And optics is now in the rearview mirror. So try to squint and see it and keep up with it. Again, PLC 6 is a review, and that's for Friday. Easy one to let slip through the cracks, so just go ahead and you take a bit of time. Hopefully it's useful for you. And don't forget Celebration 1 and homework 3 are going to be due on Thursday of next week, which I believe is the 12th, because we've got another Friday the 13th. I think that happens pretty often with February and March. I think, yeah, I think it does. If you got one Friday the 13th in February, you get another one in March. But anyways, with that, I will bid you happy rest of your day. Have a great weekend, and hopefully you enjoy the lab activity that we're going to throw your way coming up tomorrow. All righty? That's it for now, folks. Ciao.